Welcome. This presentation is about GRADE, our framework for generating realistic animated dynamic environments for robotics research. Currently, available robotics simulation tools are arguably limited in various aspects. Most of them lack visual realism, ROS integration, the capability of loading rigid and non-rigid dynamic assets, and do not offer any customization or low-level control over the simulation environment itself. Those four aspects, combined to the difficulties of collecting real-world data, are a great limiting factor in various research topics which are related to perception information. Moreover, datasets are an offline processing tool which cannot be used to test autonomous robots that need to actively perform actions. These are the main reasons why currently a lot of research is carried out with a semi-static environment assumption. However, our world is clearly dynamic with humans, children, animals, and objects that move around all the time. This affects many core functionalities of robots like visual odometry and autonomous navigation in dynamic environments, impeding progress towards autonomous robots. To solve this problem, we decided to develop a novel open-source system that focuses on four main components. The first is visual realism to reduce the sim-to-real gap. Second is the full controllability of the simulation to allow any kind of research customization and possibility of expansion. And then full ROS integration to have an easier way to deploy our code to robots. This, while having dynamic rigid and non-rigid objects in our worlds. From these four cornerstones, we developed GRADE, which is our system for generating realistic animated dynamic environments. By keeping a focus on robotic research, we developed a framework built upon Isaac Sim and Omniverse that shows how easy it is now to have simulated ROS-enabled, fully customizable robots in realistically rendered dynamic environments. Our pipeline not only includes samples of how you can get environments and other assets from various sources, but shows how you can generate data, process it, randomize the simulation conditions, and much more. Our system consists of various building blocks. We have the environment creation and processing part, the dynamic assets generation and placement module, the robot configuration, customization, and control steps, and the main simulation control tools, alongside the processing and post-processing blocks. The first step is loading and eventually randomizing an environment, including customizing light colors and conditions, textures, and reflection properties. The environment can be created from scratch, downloaded from an online source, be a digital twin, or converted from applications like Blender and Unreal. Then we must be able to load our custom robots and control them in any condition. We can load just one or multiple robots with a fully customizable sensor suite. We can control them with and without ROS, and with or without physics. We also built an easy-to-use and easily expandable custom 6 degrees of freedom joint controller to control drones or any other kind of robot that you may have which is not supported by Isaac. Third, we need dynamic assets such as humans, animals, and flying objects to increase variability. We can place these either manually, in predefined positions, or with our placement strategy that can account for the full 3D occupancy of the animation. Finally, we can control both the rendering and physics step, decide exactly when and where to publish information, and have complete control of the simulation, including any software in the loop that we may need. To complete the pipeline, we developed several tools, including a way to add custom noise profiles to ground truth data and exactly repeat any experiment while adding new sensors or obtaining new information of the same run. With all this, we generated a dataset to demonstrate the usefulness of our method focused on indoor dynamic environments. First, we converted environments from 3D front using Blender. Then we used our developed converter for simple-based human animated assets to get both cloth 3D and amassed dynamic humans. Then, using a set of custom tools, we load the environment, place the humans avoiding collisions, add flying objects, load the robot, and autonomously explore the environment using fuel. We recorded 344 sequences with corresponding ground truth data, including IMU at 240 Hz, bounding boxes, semantic instance segmentation, and much more. In order to assess the usability of the data we generate for robotics applications, we decided to evaluate SLAM methods developed specifically for dynamic environments. To that end, we selected various state-of-the-art frameworks and used them with some of our generated sequences. Some of the results are reported in this table, and as we can see, most of these show good performances in a static sequence, meaning that the data is usable. However, we notice how all of them actually fail to track the trajectory of the robot when the environment is dynamic. This happens either with very large errors or by not being able to recover after a tracking failure, as in the Dynaslam case. To test the realism, we proceeded training both YOLO and Mask RCNN. Here we will show only the results obtained with YOLO. For our tests, we selected a subset of COCO called S-COCO and a subset of our synthetic dataset called S-grade. Despite our work was not focused on super realistic humans, when pre-training on S-grade and fine-tuning on S-COCO or full COCO, we obtain performance that are better than the corresponding model trained only with real data. However, we want to stress the fact that COCO is not the best dataset to compare against due to the different scoping of grade data, which is for now solely based on indoor dynamic environments. For this reason, we labeled 4 dynamic sequences of the TUM RGB dataset, accounting for 3,500 frames, to compare with something which is more close to our domain. In this case, when comparing S-grade with S-COCO, we already show comparable performance. This despite not using any real-world image. Here as well, once we fine-tuned with COCO, we overcome the vanilla network. Finally, to prove the flexibility of our system, we tested some other scenarios such as zebras in an outdoor environment by manually placing them in the simulation and with the robot following a predefined trajectory without any ROSE intervention, an outdoor city environment where we randomly place 100 humans, and a multi-robot scenario in which 2 drones and a ground robot perform active SLAM independently. To conclude, in this work we introduced grade to solve the limitations we had with currently available simulation tools and to be able to realistically simulate any dynamic environment for robotics research. With this, we also showed current limitations of state-of-the-art dynamic SLAM systems while proving the realism of our synthetic data. However, we still miss many components. Indeed, we need to expand grade to model interactions with the environment, include more diverse and realistic assets, and much more. That is also why we make available the data we generated, our trained models, and open-sourced all our code base and invite you to check it and actively participate in that to further improve this system. Hope to hear from you soon, and thank you for your time.